Welcome to the Passive House podcast, brought to you by Passive House Accelerator, a catalyst for zero carbon building. For news, inspiration, and connections from all flavors of Passive House, check out passivehouseaccelerator.com. Sign up to receive regular updates about events, get your technical questions answered, and contribute to the community forum. There's loads of free information for experienced professionals and people just starting out on their Passive House journey. We hope to see you at one of our construction, tech, or weekly Global Passive House Showcase webinars. In the meantime, here's this week's Passive House podcast. Welcome back to the Passive House podcast. I'm Matthew Cutler-Welsh, coming to you from Auckland, New Zealand.
And I'm Zach Semke, coming to you from Seattle, Washington.
How you doing, Zach?
I'm well. I am in my new little office in the Fremont neighborhood of Seattle, which
Nice.
Immediately adjacent to the statue of Lenin that happens to be in this neighborhood in Seattle. That's currently, the lapels are painted the blue and yellow of Ukraine.
I'm sure he would have appreciated that.
Yeah, I'm sure he would. I'm sure he would have. And it's raining a little bit today, so it's definitely feeling like autumn, as they say in New Zealand.
Yeah, nice fall, springtime here, and we've just completed a housing summit here at the New Zealand Green Building Council, which was a very successful event. 230 people, which is a good size for that type of event in that industry here, and a lot of talk about carbon. There's just so much going on in the construction industry around both embodied and operational carbon, and it's really interesting to see people start to learn about that, start to understand some of the international frameworks that are becoming standard practice, and how that gets implemented through the financial sector down through architects and builders and building owners. So there's a lot of pace picking up there, as well as all the other really good stuff, and the common themes around health and energy efficiency in homes. Another big theme, which we're just kind of starting to talk about, is what to do with existing homes. And so we had an awesome international speaker virtually from the UK talking about Energy Sprung, and the thing I liked about that, because I think you've had some of input from Energy Sprung on Passive House Accelerator, was that she talked about how they had learnt from the experience in the Netherlands, and I'm a big fan of learning from what others have done rather than reinventing the wheel, and that's kind of the Energy Sprung model, which it's just growing, that modularized, systemized retrofit program is really, really cool.
That's all exciting stuff. Yeah, the Energy Sprung model also seems like it'd be super applicable in the UK, where you also have those tracts of I don't know if they're called townhomes in the UK or not, but developments where, similar to in the Netherlands, you could apply a given solution over and over and over on the outside of the building. Yeah,
a lot of row houses and kind of similar constructions. So it's pretty cool, but it's a big task. She said that if to achieve their goals by 2050, at the start of the program, they needed to be doing about 2 houses per minute for the next 30 years or something, but because it's hasn't been that fast, they need the number's gone up to now 6 homes per minute need to be retrofitted in order to achieve the carbon goals. So that's kind of a really good visualization of the scale of that challenge.
Yeah, it's a little stressful.
Anyway,
to think about that.
We've got a building physics masterclass to
indeed
present today that you had with Mark Siddall.
Yeah.
So we should get into that as fast as we can. So let's thank our sponsors and then get into it.
Yeah, let's do. So our founding sponsors are 475 High Performance Building Supply, Baxt Ingui Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stillcorp, and Zola Windows. Thanks too to our champion sponsors, Icon Windows and Doors and Proseco. And thank you to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority.
Awesome. Well, this is a big one, but there's so much great stuff in here. Mark is I don't know how he gets time to do his architectural work alongside all this other great content and research and writing that he does. He has been a guest on the show before.
That's right, episode 52.
And also an episode of the Live.
Yeah, that's right. He presented about Large Corner, I think a little bit, probably about a year ago.
Yeah, I think a lot of people will either know of him, or if you don't know Mark and haven't heard or read something of him knowingly, you there's a good chance if you're working in Passive House world, you will have come across some of his work. I know he's produced some excellent resources for people who are studying to do their Passive House training as well. So he's just a prolific content creator and researcher and quite a good communicator of some pretty technical concepts as well. So let's jump into it.
Yeah, let's do. So this is Mark Siddall. He is with the firm Leap, and we go into an introduction at the beginning of the interview. So without further ado, here's Mark. Well, welcome to the Passive House podcast, Mark Siddall. It's great to have you here.
Thanks for having me, Zach. It's a pleasure to be back again. Indeed.
Yeah, you joined Matthew for an interview back on, I think, exactly more or less 1 year ago. Probably It was episode 52, and we're at episode 106 now, I think. So it's great. We'll have to have you again in September of 2023 as well.
Yeah.
So Mark, you are an architect, founder and director of low energy architecture at LEAP, which stands for Lovingly Engineered Architectural Process, which I think is a wonderful name. And for listeners who want to learn more and dive deeper into your work, especially the Large Corner project, the episode 52 is a great resource, as well as your presentation on Passive House Accelerator Live, which was, I think, last October. So we'll share links in the show notes for that. But for folks who are brand new to your work, maybe we could just start, and we're going to dive into this amazing report that you've just produced. But before we do, if you could just give a little bit of an overview of your practice and also your involvement with Passive House Trust.
Yeah. Okay. So I suppose I first stumbled into Passive House around about 16 years ago now. And at that time, there was no English materials out there. So I was using Google Translate quite a lot to understand Passive House and what it was for the UK context, and trying to understand even whether the physics worked in the UK, should we say, because of all those skepticisms that, those kind of processes that we go through when we're dealing with something new. But lo and behold, I kind of each time I kind of prodded it, it kind of remained robust. And I've kind of done various different things to challenge it over time, as other people have, and it keeps working. So that's always reassuring. So after having worked on a project where we, previous practice that I was working for at the time, we did 25 passive houses, the largest development in the UK briefly, now totally eclipsed. Thankfully, really, it's a good thing.
Exactly.
So I then ended up setting up my own practice, because the writing was on the wall, should we say, for the practice, for where I was working. It was kind of go back to the old ways, and that didn't work anymore. So I ended up setting up my own practice, and there's now 3 of us working on new build and retrofit homes. So we're kind of very much in the residential sector at the moment, but we're looking at started to work with some local authorities, as well as predominantly homeowners and self-builders and people that are doing their own thing. In terms of the Passive House Trust, I've been a technical advisor at the Passive House Trust for near enough the beginning, should we say. And then I'm also a technical advisor and trustee of the ACB, which is the Association for Environment Conscious Building. I've always had a technical background. I trained as an architectural technologist before I trained to become an architect. I think that sort of puts me in good stead for Passive House in many respects.
Right. Yeah, that makes sense. Well, thank you. That's a great overview. And again, check out episode 52 for more. So we're going to dive into a report that was just published by Passive House Trust, right? It is now on the magazine stands or whatever the virtual.
That's it. It'll be on a website near you.
That's right. And it's entitled Thermal Bypass Risks, a Technical Review. And this is a substantial, very well-cited piece of work. And I think it clocks in at just over 60 pages. It's full of detail. Readers can dive into your review of the literature around thermal bypass in buildings, convective loops, wind washing and permeance of surfaces, wind and air barriers. And I really appreciate that each section has several practical implications, call-outs that guide the reader, especially non-technical readers like myself, to what's important as takeaways. And then you also have a really great end piece called the REBA Plan of Work that provides real straightforward design guidance. So I highly recommend folks check out this report and dive into it. And I'm really pleased that we get to discuss it today on the podcast. So could you start with kind of what was the why behind this project? What is the motivation for putting it together?
Yeah, well, there are a number of different motivations, I guess. One of them really speaks to an environmental issue in terms of, if we're using more energy than we need to, then we've got to get our act together. There's also what I believe is a matter of professional integrity, shall we say? One whereby any self-respecting architect, in my view, should be concerned that their buildings are performing as they were designed. If there's a performance gap, then this is not a position to be in. Even if we just put it down into you could be sued, your professional indemnities on the line, those kinds of ways of thinking, that's a concern. But at the end of the day, performance gaps and failures in building performance have just been a niggle for a long time. I wrote a much shorter document, article on thermal bypass 10 or 15 years ago. But this new document really goes into the weeds, sets it all out, and we've got to define what we're talking about. In a sense, we're talking about this subject of thermal bypass, but what is it? It's not necessarily a subject matter that's familiar to many people. So really, if we go back to the original research from Princeton University, then the definition of thermal bypass in a scientific sense or in a physical sense is thermal bypass is heat loss that bypasses the conductive and radiative heat transfer mechanisms. And when you kind of finally get through that, what we're really talking about is air movement, any kind of air movement, in and around and through and behind and anything, insulation. That's what we're dealing with. And we talk about air. There's several things to that. Air tightness is one that we often talk about. It's very kind of much within the construction industry's kind of language. But what we've got to recognize is that there are two main forms of thermal bypass. There's open loop bypass and closed loop bypass. Open loop bypass, air tightness is one of those mechanisms that is, or sits under that category. The other one is wind tightness. And then we've got closed loop bypass, which is convection air movement within a fixed cavity space. So you can get perhaps the easiest way to visualize that is within your double or triple glazing. You've got those air cavities, and you've got an air loop kind of going round and round as the warm air rises and the cold air falls. But then we can get those in construction cavities as well, where in those zones where we've got insulation, and that can undermine the thermal performance of a building as well. So those are the so there's really those kind of three key factors that we're thinking about. Closed loop convection, within a cavity, wind tightness and air tightness, and then there's all manner of ways that we can get it wrong, and that's what this report really looks at in terms of trying to look at all of the peer-reviewed research. And there are no real viewpoints, I'd like to think, in this document. There's very little conjecture. There are a few areas which we'll touch on, where the research stops, but intuition points in certain directions, and I've tried to fill in the gaps so that we, as passive house designers, can make informed, intelligent decisions about what we're doing. Until the right research comes along and either disproves my conjecture, which is great, or hopefully or proves it, in which case then we're at least on the right track. So yeah, that's where we stand at the moment.
Yeah. Well, should we dive into the first of the thermal bypass categories? And this is, I think you've kind of outlined also the structure of the paper, which is really useful. So that first one is convective loops in wall constructions. So what did what did the literature say? And, what are the risks, and, how do we address them? I'd love to hear you talk about that.
So a lot of, okay, so in terms of dealing with convective loops in kind of air movement in cavities, the thing that we've got to think about is the construction industry is endlessly creative, and there are ways that we can perfectly suspend pieces of insulation in the cavity in such a way that virtually they don't, the insulation goes to no use at all, because we've got gaps. So there are different interfaces that we need to think about. We normally talk about a cavity, and we're all familiar with cavities in construction. We put a cavity in there as a capillary break to let rainwater get kind of not interfere with the rest of our building. But when we've got those unintended cavities, and I've described those as air gaps, they're on the warm side of the insulation. And really what we would like to think is that if we've got a warm body of air on the warm side of the insulation, that shouldn't be able to get through to the other side, or out the top or the bottom. But unfortunately, we find ways to do that. We either insulation boards have got a limited length, so they have a joint at an interface, and then unless it's perfectly butting up, we've got some sort of air gap. And if that air gap goes from the cavity through the joint and from the cavity through the joint and into the air gap on the warm side, then we've got that opportunity for air movement and significant types of air movement, because the wind can wash through and cause movement. But also we've got just warm air convection, heat loss from the property into this air gap, that then warm air rises, which then entrains, draws in colder air from the cavity space just by natural convection, and then we've got more heat loss taking place. So all of the evidence that we've looked at, there are numerous different studies looking at masonry build, timber frame, and cavity wall construction and the likes, and there are innumerable ways that we can get it wrong. So where we start to get into some of the more shocking kind of statistics is where we start to think about. I'm just going to give you a few kind of overviews here. If we've got a 2 millimeter wide gap on the air gap, this is on the warm side of the insulation, then if we're dealing with, and you'll have to forgive me here, I'm going to use European heat loss metrics, U values. If we've got a U value of 0.15, so that's very, very low, that's passive house territories of construction, then we would expect the heat loss to have increased by around about 17%. Okay, and that's just with a 2 millimeter wide gap.
2 millimeter.
So that's the width of a coin.
Tiny.
Okay,
Yeah.
You can drop $1 down there or whatever you want, but
Right.
you can. If you can slot a penny coin in there, then you've got enough opportunity for some kind of air movement to take place. And then if you're in the UK, where we often see a cavity wall construction going on regular building sites, so not passive house, then you can be walking past a building site and you'll see a 10 or 15 millimeter air gap at the back of that. Yeah. And if we had our theoretical passive house construction, then so a 7 millimeter wide joint air gap, I should say, would lead to a 244% increase in heat loss, according to my kind of rough and ready calcs. Yeah. Whereas a 15 millimeter gap, and this is where you're sitting down now, a 680% increase in heat loss. So kind of it just basically means your insulation is doing nothing. If you haven't got the quality of workmanship in place, then it's not going to happen. Your insulation won't perform properly. However, I'm going to be careful when I say workmanship, because it's very easy to denigrate the trades, and those guys and gals are doing the best that they can do. And if we architects have given them a crap specification, then they're in a really problematic situation. So the example would be if you're again, in the UK, masonry cavity wall construction, we're often using foam, rigid boards. And then you're using block work with mortar joints. Mortar is squidgy originally, until it cures. And therefore you get mortar snots projecting into the cavities, and they create these perfect gaps, that are in that 7 to 15 millimeter range.
Right.
Because of the little bits of mortar projecting into the air gap zone. So it sets up this kind of perfect mechanism for this kind of heat loss.
Yeah.
So it was those kind of things that really sort of set my mind alive. And it was like, hang on a minute. If this is, if based upon the research that's been done and we project that for passive house types of construction, what should we be doing and how should we be designing appropriately? And what kind of gaps can we get away with, if we can get away with any gaps at all?
Yeah.
So that's sort of where we sit.
And so what did you find? I mean, what are the best practices for addressing, avoiding these gaps?
Well, one of the things that I did as I was trying to figure out what parameters have we got, what engineering tolerances are acceptable. I actually found some research from Norway in about 1996 by a researcher, and I'm going to slay his name, unfortunately, probably Usvlok is how I'm pronouncing it. And if he ever listens to this podcast, I do apologize. He positioned that we should, in one of his bits of research, that we should be limiting excess heat loss, so stuff that we can't account for in a calculation, readily. We should be limiting the impact to less than 5%. And that seems a reasonable engineering tolerance. If we got 5%, the other people suggested 3%. So we're in that sort of 3 to 5% range. I just said 5%. Why not? Made up number as far as I'm concerned. But what we want to be able to do is have confidence that if we can't do things perfectly, we're dealing with a range. So what that sort of tells us is that that starts to then inform the parameters for all of the specifications that we might think about in terms of how big an air gap may be acceptable, where it may be, or what it's doing. And the easiest thing to recognize here is that basically we need insulation to firmly abut the warm side. That's the most abundantly clear thing from the research. That absolutely has to happen. Or at least the cavities at top and bottom of that air gap have to be sealed, and all the joints have to be sealed as well. We don't. We want to prevent any convective loops taking place. So the most important thing that we've got to do is make sure that the insulation is tightly abutting the warm side structure, or whatever that may be. So that way we don't have any air gaps. Because if we do have air gaps, then there's we've got these bypass risks. And if for some reason we can't prevent those air gaps happening, perhaps the surface that we're dealing with is uneven in some sense, then what we need to do is make sure that the gap at the top and bottom of the air gap and the flanking sides of the air gap are also sealed.
Encapsulation.
I'm avoiding more using the word joint there, because a joint in the definition in the document is basically the interface between two pieces of insulation. Where we might have two boards abutting one another, so that's a joint. So within an air gap, there are these points where edges that we also have to kind of contend with potentially as well.
Got it. Yeah. So and how does this impact the trades then? How do you see this then translate? I mean, clearly the encapsulation piece is a design piece. How do you ensure that the insulation is abutting that warm side?
Well, this is where we've got to think as designers. We've got to start paying some attention, really. If we're dealing with cavity wall construction, then we've got to make sure that the mortar snots get cleaned away, so that we've got a relatively flat enough surface. We've got to then make sure that we're using the right kind of insulation that can work with an uneven surface. So that would suggest that would be a mineral wool insulation. The peer-reviewed papers cite using mineral wool. They also cite as an innovative product that is yet to be manufactured, whereby there was a bit of mineral wool on the back of some foam insulation, perhaps. Whatever happens, something that can absorb those undulations and irregularities in the surface. But we can start to take that another step further when we start to think about how do we define flatness and surfaces, so that and this might become more prevalent on a larger building where we've got large sheet boards that we're dealing with that are facing into a cavity. And here we're thinking about non-domestic construction, perhaps, rather than something that might be I-beam construction or whatever it might be in the passive house context for residential sides of thinking. So if we've then got large sheet boards that we're dealing with, how flat are they? Well, the flat, they can bend, they can twist, they're going onto some sort of substrate, some sort of secondary structure. And how are the joints? All of these questions start to crop up. So we need to start to think how we specify that. And I'm not saying that we've got all of the answers, but in terms of that I've got all the answers to all of the technologies, but we do have performance specifications that we can use now to start to inform how we think about a design. And we can engage in these conversations with each other, with our colleagues, through the passive house networks that are out there. And we can, as the community overall, to start to figure these things out and understand how we can do things in ways that we can be more confident of.
Right, and bring some intention around this, which is probably hasn't necessarily been top of mind before now. So, and what about overstuffing? I know that was something you were also addressing in the report.
Mm-hmm. So, I mean, there are certain types of construction where you can do a little bit of an overstuff. And so first of all, what is an overstuff? That's putting in a little bit more insulation than you should do, from a standard calculation point of view, to hit your U value or your R value. Now, but we don't want to put too much in. If we put too much insulation in, then we're effectively going to turn something into a solid at some point, and it'll be more conductive than we want it to be. So it's only just a little bit. It was 5 to 10%, just enough of squish and squidge, so that it's pushing back. Now that works when you're dealing with timber frame, where you might be sandwiching between two boards or a couple of membranes, and you can afford the insulation to push back. But when you're dealing with something like cavity wall construction, masonry, well, there's enough force in insulation that it could actually push your mortar joint over, because it's still setting. Right. So we've got to be careful for the construction technologies when we use an overstuff. So it's a general principle that we can use, but increasingly those people that are more concerned about ecological construction are tending to move towards more timber frame construction where they can. And then there are other areas, I know in Canada and the States, timber frames and other parts of Northern Europe where timber frames very prevalent in the first place anyway.
Right.
So yeah, we've got to think about what we how we can specify insulation to try and avoid these air gaps. The other thing that we can do, if we can't use an overstuff, is we need to find ways to mechanically fix and push the insulation back against that warm side, so that so there's kind of pull strengths and all sorts of other things that I don't know enough about, structural engineering sides of things we need some more testing to see what kind of pull strengths we're on about and how much force is certain bits of insulation exert. Some experience that we've had working on retrofits is that it's okay if you've got kind of 50 millimeters of insulation or even 80, you can just about bend those big boards. But when you're dealing with 300 millimeters of insulation, that's not flexible anymore. So
Right.
you've got to start to that mechanical fixing really becomes more important to make sure that you've got a decent substrate that you're fixing onto. Or that you've got some sort of bonding agent across the back of the insulation, so that when you do offer it up, it does adhere and create those kind of nice sealed air pockets. There's different. External thermal wall insulation been a good example. They'll take a big foam board and as long as you've got a continuous strip of insulation around the outside edges, of bonding agent around the outside edges of the insulation, then you can avoid that air movement and mitigate the risk of thermal bypass as much as possible.
Sure. Well, great summary here. Is there more on convective loops that we want to address before moving to the next piece of the report?
I think well, when we're dealing with timber frame, or when we're tucking insulation into a structure, often we end up seeing tuck ends. So that's where the insulation at the edge, it's abutting the studs, the structure, and we see that think people have pushed it in naturally, because that's how you're going to you're pushing something in, and it squishes on the edges, but that's not a good thing. Those little tuck ends, they might look fairly inconsequential, but they actually again allow these convective loops to start to kick in, or insulation that's missing at the top and bottom allows that those loops to take place as well. So all of those little gaps can kind of join together and create more opportunities that are not as significant as the scary stuff that I was talking about, but it still exceeds our 5 to 10% threshold that we would consider good practice. I think that tuck ends are kind of another area that we need to pay closer attention to. And at the end of the document, I've stolen some stuff from ResNet and then tweaked it for a passive house context, whereby it's got a simple elevation of a couple of stud walls, and I've tried to use that as a way of describing what tolerances, should we say, if we're doing a visual inspection on site, what might be okay. It becomes how can we inform site foremen, site managers, and tradespeople themselves, so that they can self-inspect and the likes, because dare I say, architects can't and the likes can't be on site all the time. We only ever it's almost like my analogy is it's like a ball in flight. If you video it in stills, we're only there to capture the stills, but we don't get the bits, the time in between those stills.
Sure.
So that's site visits for you. So we need somebody on site that's got closer contact. So they're watching it in high speed, shall we say? If catching, they've got more stills in there to fill in the gaps.
Absolutely. Well, should we dive into wind washing and permeance of surfaces?
Yeah. So I think that a lot of us are somewhat familiar in the passive house circles, at least, with wind tightness, the concept of wind tightness. Now, the purpose of having some kind of wind tightness, whatever that may be, in terms of a standard, in terms of what target should we be pursuing. But the idea is that we're stopping the wind from blowing through the insulation or around or behind the insulation, and again, kind of undermining this thermal performance. And this forced convection, as it was described in a kind of a physics sense, is what we need to be most concerned about. Simple natural convection, warm air rising, is a problem, but it's not. The wind can rip through things so much more significantly. So when we're starting to think about this, things like the geometry, are we, and the location of the building, is it a tall building? Is it a short building? Is it in a prairie, in a greenfield location, or is it in a suburban location or in the middle of the city? All of these things are going to have an impact upon how we might ultimately consider the impact of wind washing and the likes. But with us, so just as a kind of a point of reference, 2 pascals, okay, it's not a lot of pressure. If you take I'll be using metric here, I'm afraid, but if you take a sheet of photocopy paper, decent quality photocopy paper, that's about 100 grams a meter square. And so we're dealing with a couple of sheets of that paper, meter square. Right. That is 2 pascals worth of pressure. It's not a lot. Well, that's the amount. 2 pascals worth of pressure is what we get on the ceiling of a 2-story house. And as we'll know from all of our passive house training, if we've got a 1 millimeter wide gap that's 1 meter long, we'll get around about 350 grams of moisture traveling through that during the course of 24 hours, when it's about 0 degrees Celsius inside and 0 outside, 20 in, and 50% relative humidity inside. So that's a lot of moisture that's, and this starts to allude to where we get on to talking about air tightness. But I think that those stack pressures and wind pressures are what we're trying to deal with by having having that wind tightness kind of membrane in place. So what we've then got to think about is if we've got a wind tightness concept, okay, it's not a product, it's not a membrane necessarily, it's a surface right now we'll say it's of infinite dimension. It's just a surface, and we want to stop the wind getting through it. The question then starts to be, well, what dictates how good that insulation, that wind barrier needs to be? It's it's not the wind speed outside necessarily, it's the velocity of the air within the cavity. And what we can say is that, well, maybe there are certain types of insulation that can withstand an air movement across it. We've got nice fibrous, fluffy stuff. We've got the really, really light stuff, which I understand that in America, fiberglass is used quite widely, or at least it was in the papers that I've reviewed. And that's really, really light, and the air can push through that very easily. And if that's exposed to the wind, it's shot. That's what that's a simple summary of the research. But if you've got something denser, then it becomes more resistant. It's got a higher permeant. It's less permeant, air permeable. So then we can push that up to a certain density of insulation that's appropriate, that could act as a wind barrier, or we can use wind barrier, or we can use membranes to do the same job, depending on the circumstances. So we might find in residential construction, wind barrier membranes are a good port of call, should we say. We can use blown fiber insulations, recycled cellulose, recycled newspapers as cellulose or whatever it may be. But if we're putting bats or rolls in, then we can use that slate over stuff onto with a wind tightness membrane, and we can get some good things going there. But on a larger non-domestic building, putting it where you might end up with helping hand brackets that hold up rain screen cladding systems, it becomes very difficult to then include a wind tightness membrane, because we haven't got continuous bits of battens on the outside that we can fix to and do all of the things that you might do with a siding, as you'd say in the States. So where we've got a rain screen on a non-domestic building, maybe it terracotta or whatever the architectural fancy may be, we've got these brackets that are fixing through and tearing great holes in our membranes, and also forcing open joints of some kind into our insulation. What do we do then? Well, there's some good research that's been done up in Canada by our good friends at RDH that looks at using dense mineral wool insulations exposed within the cavity. But what we've got to be mindful of, again, is where we've got these joints and interfaces and helping hand brackets, and how they can create links that could get through to that air gap on the warm side again. So we need to think about how those joints might be sealed. And there's not really any research on that. So we are now at the cutting edge, and we are sort of trying to puzzle it out, shall we say, amongst ourselves in a live conversation. And some of the thoughts that I've had, conversations I've had to date with people like Nick Grant, who I think you've probably spoken to in the past. It's a case of some of these paint-on air tightness paints that we can use on a masonry construction. Can they be painted onto these joints to seal those joints up and make sure that they would be suitable? We've got to think about fire and other risks like that, which is why mineral walls and the likes are useful in large multi-story buildings. Or the other way of thinking is that a lot of these mineral wall manufacturers also do external wall insulation rendering systems. So perhaps we just need to be able to put a little bit of a parging coat render strip over these joints so that we've got we reduce those risks. It'd be great if we had tapes, but they don't respond so well to mineral walls and things like that. They'll come debonded over time. So that's the most challenging cutting edge questions that this paper asks and hasn't fully resolved, because there's no research, and I'm not really trying to get drawn in on conjecture, shall we say, or trying to base things around a sound evidence base or intuitive engineering that we can be, that we're kind of quite reliable with for the time being. And of course, as buildings get taller and taller, then the velocity of air in the cavity can increase. Because you've got more stack pressure that can take place, because obviously on the outside of a building we've got the sun shining, and that can and where the sun's shining, it's warming up that cavity, and therefore we can get much more natural convection, more buoyancy. So so sometimes the wind's dominant, sometimes it's those it's kind of solar driven natural convection that we're trying to deal with, but we can specify. Because we know the velocity of air within cavities, there are some peer-reviewed papers that have kind of started to establish that. It means that we can then start to infer what kinds of densities of insulation could be exposed within a cavity, or the research from Norway was looking at how wind tight a membrane system has to be. So again, this goes back to my old champion Usvlok. He's a very generous guy, by the way. I emailed him cheekily, cheeky emails to researchers from around the world and to see what comes back. And he very generously sent a couple of papers just this last weekend, which is actually going into an update of the paper before pre-release.
Nice.
So some things we'll touch on a little bit later on natural convection in insulation materials. But he, Usvlok in 1996 proposed a wind tightness standard for Norway. Because their research looked at timber frame construction and identified that this wind washing effect through and behind and around insulation materials and how that could degrade thermal performance. So that led to this a wind tightness target, which is measured in permeability. Which in passive house worlds we're often using air changes per hour. Nick Grant and I and a few others in the UK. In the UK, we use permeability. So this is based on surface area rather than air changes per hour.
Right.
And we actually think that that's a better register for understanding the performance of the building fabric.
FIAS certification has gone that way as well to the permeance. Yeah.
Okay. Yeah. So it's good. It's good from a building fabric perspective. It throws up other challenges because when you're starting to do heat loss calculations. So air changes per hour are kind of like good for heat loss calcs. Permeability is a good way of thinking about the building fabric. They're both useful. I would. Right. I think that they both have their place to some extent. Where we start to get to is this research by Usvlok and the kind of proposed wind tightness targets that were developed, and that was when you're seeking to limit heat loss by having a wind tightness target. The way that Usvlok did that was he measured the heat loss through the insulation and the wall constructions, set a target value of less than 5% impact on his U value. And then you say, well, we've changed our U values now. We're not dealing with the old U values from 1996. We're now dealing with something more advanced, so, lower heat loss. So therefore, that intuitively tells us that wind tightness target that was used, we can't just take that face value, which was from memory, it's around about 2.5. Okay, we can't just take that at face value, because our U values, our heat loss, our values are that much lower or higher than they were in the past. So we've got to correct for that. And so I've done some rough and ready rule of thumb, kind of, if all things being equal, architects on physicists, should we say, calculations, and said, well, if I know how much heat loss there was through that wall construction, what should we be trying to do in the future? So we've got a table that then sets out for different U values what our wind tightness target would be. Now, it's important to recognize we can't really measure wind tightness. We can measure if you did an external air wind barrier, you could, potentially, in a sense. But as we might get onto towards the end of this conversation, there are reasons why we might not want to do external air wind barriers. But if all things being equal, if we've got an air barrier on the inside, we can't measure the wind tightness on the outside. But what those numbers start to speak to, as passive house designers at least, is the standard of workmanship, and it starts to look quite similar to the standard workmanship that we'd look to on the outside of a building. On the inside of a building. So our eyes as passive house designers, we're intuitively positioned to be able to go, if it's, we know what we'd expect on the inside, and if it's been done on the outside, we're okay. And it's a rule, so it's kind of like an engineered framework to give you a rule of thumb approach. So that's sort of where we end up in terms of looking, what we're looking to do. And the other things to recognise is that there are certain locations that are more important to make wind tight than others.
Right. Yeah. And
this goes back to a geometry kind of thing. So whilst we might have our surfaces, at a decent standard, we've got to pay real attention to corners and edges like eaves or ridges. Those kinds of positions are more prone to catching the wind, either with a positive or negative pressure, and therefore are more likely to fail, for want of a way of describing it. So whilst we want to make so those are the places that we really want to focus attention when we're checking wind tightness and inspecting things on a building site.
Excellent. And the numbers, the kind of metrics that the Norwegian researcher was putting out there seemed consistent, if I remember correctly, with kind of the requirements for those more problematic areas, right?
Yes. So there was there's two Norwegian researchers that have looked at wind tightness. Right. One, Usvlok was one, and the other gentleman's name, or a couple of people that the paper, that contributed to papers. Their names are escaping me now. But there was a good agreement within their research, so we can have quite a lot of confidence that Ojanen, if I pronounce that right, Ojanen maybe, I don't know. Yes, he'd looked at different corners and edges and sheltering factors and the likes, and there was a reasonable amount of commonality there, which can again give us confidence for just having a single number and in our mind's eye for our inspections. So yeah, excellent.
Well, should we? Go ahead.
No, I don't know how. We've got, so we're talking. I'm thinking quite a lot about walls as I'm talking. One thing that we haven't really touched on is roofs.
Oh yeah.
So
right.
So the thing here
piece of the
is
paper.
where we're dealing with a warm roof or a cold roof.
Mm-hmm.
If it's a warm roof construction, then everything is still encapsulated, and all these same kinds of criteria that we've been talking about kind of apply. But where we've got a cold roof construction, this is where we start to get into, well, we might be blowing fibre insulation into a cold roof construction. So what kind of air movement across that insulation is acceptable? Is all, we need to have information about what kind of velocities of air move within these kind of larger cavity spaces, which will be triangular roof spaces. So there's natural convection and there'll be some wind coming in from the edges if we've got a ventilated roof structure. So that leads us to, how do we protect from the wind? UK construction is problematic. We don't have. There's a component in that you can see in Swedish literature, for instance,
there's a diagram in the paper of this.
Vindavlär, I think. Again, this is a dyslexic trying to read Swedish. It's going to go wrong. But basically, it's a wind deflector, and we don't have wind deflectors. We have ways of getting ventilation into the roof space, but we're not really bothered about protecting the insulation from wind washing. In standard UK construction details, this is. So we need to think about how we detail that. Now, where that's led me to in passive house design is that I now design unventilated roofs, which is counter to a lot of the construction industry's thinking. Because they're going to go, that's stupid, for the right reasons. Because what happens when the moisture does get up into the roof space?
Right.
Well, you make sure you've got an airtight building and you detail it so that it's got sufficient robustness that it won't leak at a later date. And I've managed to get some funding. So I did a bit of research a couple of years ago, and we measured the moisture levels in an unventilated warm cold roof, done the way that I do it, shall we say, and we found that it was safer. The wood was going to be drier than it would have been if you'd have just left it outside under a tarpaulin, because of solar gains. So there are ways to deal with that, but it's, again, we're on this edge of understanding here. But there's some great research. There's a paper that I did, which I don't think I think it is referenced in this, where we're talking about the air movement and warm, unventilated cold roofs. But the key thing there is making sure that if we have got a ventilated roof, that we have this wind deflector in there, and that this wind deflector extends beyond the face of the insulation by about a foot in old money, 300 millimeters in our world. So that way, as that wind blows into the loft space, it's got the chance to slow down, and it won't rip itself through the insulation and dislodge or move the blown insulation, perhaps in some cases. So that's kind of a bit more on our. So we've talked about wind tightness as a target, as a standard, and we've talked about how we might deal with those cases, those roof constructions that are where a wind tightness target is harder to implement, shall we say.
I really felt like the diagram that was, and this is jumping into airtightness, the diagram that was comparing, basically different strategies around airtightness and where in the envelope it should be. Should it be, on the warm side, somewhere in the middle, on the exterior, was really effective. Could you talk a little bit about that?
Yeah, so begged, borrowed, and stolen. Didn't invent those diagrams and the way that information has been conveyed. That came from a book that was written in 1982. None of this stuff is new.
Right.
Right. I kind of, when I first started to get into trying to think about passive house and how do we design airtight buildings, there was no real useful information in the UK. Mm-hmm. I ended up getting 2 books from the British Library. Like in London, I'm in Durham, so I'm at the opposite end of the country. I had to get them basically brought up to the northeast, and I pored over them, and Yeah, basically one was Canadian, and by David Ayer. Yeah, it's uncanny that David Ayer would be working on air tightness. And then the other book that I found was from Sweden, and that was written at a similar point in time. But both of these projects really identified key things like the construction process, the sequencing is really integral to getting air tightness right. And the Swedish examples, they've got 0.6 back in the 1977. And then over in Canada, of course, we've got the Saskatchewan Low Energy House, and they were doing the same thing in Canada. So we know that this is all time tested stuff,
Yeah.
When we start to think about air tightness, what are we really talking about and why are we doing it? Well, I mentioned a little bit a while ago about this 1 millimeter wide gap and how we don't want moisture getting into our walls and our construction. We've also got to think, there was some great research that was done in Canada again, and trying to quantify what standard of air tightness would be appropriate in a Canadian climate, so that you're not going to get interstitial condensation. Okay, and basically the premise here is that you've got a relatively impermeable, retarding, moisture retarding membrane on the inside or surface on the inside. You've got something more breathable on the outside of a known quantity. And then that known quantity on the outside, it can deal with so much moisture. And then you've got maybe a bit of insulation and other things that can deal with a little bit of interstitial condensation, just enough, but not too much. So the Canadian research that was done basically identified Leonardo. I always think of Ninja Turtles whenever I read his name, but
nice reference.
There we go. His analysis basically started to derive an air tightness target that was around about 0.5 permeability. This is about 0.5 meters cubed per meter square at 50 pascals. But then at a later date that was revised to recognise that the vapor permeability of the wind barrier might vary, and therefore the air tightness target may become more demanding, because if it's less permeable on the outside, we need a higher standard of air tightness on the inside to kind of try and keep that moisture balance.
Sure.
So that's all documented in the paper as well, and seems, should we say, generally within the folklore of the building physicists, this seems to be quite well established. Everyone seems to keep going back to this, and is it John Strow over in Canada? He kind of he had to go at deriving an air tightness target as well, and that ended up in the same sort of territories. I think I've just got the document in front of me. He ended up with 0.235 as his, I think it was, that sort of territory. But that was roughly similar to the Leonardo's kind of revised figures, should we say, when he started to take into account different vapor permeabilities, SD values, for one way of putting it, on the outside. Or perm ratings, I guess, for you guys, isn't it?
Right. Ratings. Mm-hmm.
Yeah. So, all of these things are interplayed, and we talk about that in the document as well. So there's plenty more for people to geek out about, and ask questions and understand where the physical research is up to, for certain climate zones, if nothing else.
Right. And so after that geeking out, you have a section of the report that I mentioned, which is essentially advice for practitioners. It was REBA plan of work. So what were the key pieces of advice and guidance that you included in that document, and why?
So, well, as I say, there are some diagrams, useful diagrams, about basically where can you put your air barrier and your wind barrier. Well, technically, your wind barrier always wants to go on the outside, and your air barrier, we don't necessarily want it on the inside surface, because we might damage it, but that's okay if you're doing masonry. So we've got a diagram for that. Then we've got another one whereby it's slightly buried in a wall, which is what you tend to see in a timber frame construction more readily. And then there are kind of slight different variants of that. But we've got to be mindful that we don't want the air barrier to be buried too deep in the wall. We don't want it for a third of your U value, a third of your resistance. You don't want the membrane to be buried too deep, otherwise you could get interstitial condensation. So there's a few nods to that. And then there's a few hazard warnings, shall we say, as well, about trying to combine your wind barrier and your air barrier. Again, there's some really fantastic research that's been done over in Belgium, and it really highlights the risks, due to climate. So in some climates it may be okay, in other climates it could be just stupid. And the UK is one of those climates whereby you really don't want to be doing it, because if you've got any air leakage, basically the risk is that you can have a kind of a pumping action that takes place, whereby the external air barrier, wind barrier is flat, kind of undulating, sucking moist air into the wall construction, or there's some kind of convective loops that can start to arise naturally.
Wow.
And that can then distribute, those convective loops then distribute moisture across the surface of your wind barrier on the outside, and then that causes decay. So there are some risks in certain climate zones. So the conclusion really would be, make sure you're doing some proper analysis using a tool like WUFI or something like that, so you understand the hygrothermal performance and you can start to understand some of the risks. But I will caveat this: WUFI doesn't do CFD, computational fluid dynamic analysis. So it may not be perfect for assessing these kinds of risks. There are boundaries to it, but it's the kind of, if you're going to do it, play safe. And it was the key. One of the key things that came out of the Belgian research is, if you're going to do an external air wind barrier, do not use mineral wool products or any of those kind of things. Hygroscopic insulation like cellulose is okay, because that's got a bit of moisture buffering that'll get you through the seasons a little bit better. And also there's less risk of natural convection because of how it's blown into all of the gaps, assuming you're blowing it into all of the gaps, of course. That's always the challenge with blown insulations. So that sort of covers what's kind of tackled in that section. And there's one section that I'm conscious we've skipped, and that is the one to do with natural convection in insulation. So we've talked, a lot of our conversation about thermal bypass so far has been in cavities that can be around insulation, but we can also get convection inside the insulation system. It's the insulation products or installations themselves. Now, it doesn't really happen in a foam insulation, but it can happen in a fibrous insulation. So whether that's a wood fibre insulation, a cellulose insulation, a mineral wool, or of one kind, whether it's rock or glass, those kind of things, we can get convection within there. And I've been on a learning journey with this, because I can talk about Nusselt values and Rayleigh values, which I don't need to really go there. It's all in the document. But the key thing is, there's some really useful Norwegian research that I'm citing, which talks about the risks of convection in walls, in wall roof construction, and then in horizontal flat roof construction. And we can, that information allows us to understand how and if we need to add a correction factor to our calculations to account for those kinds of things. Thankfully, there are some simple solutions. If you've got insulation that's more than 200 millimeters thick, I haven't got a scale, haven't got an imperial, 200 millimeters. 6 inches is 150 millimeters. So we're talking of
9 or 10 inches,
8 inches, that sort of territory.
8 inches, 8 inches.
basically, if you've got insulation that's thicker, an insulation construction that's thicker than 200 millimeters, the Norwegian research suggests that you might actually be installing a convection barrier membrane. Now, that sounds like, oh, this is going to be a lot of extra work, isn't it? Passive house is expensive enough, or good buildings are expensive enough, and it doesn't have to be difficult. It could just be a sheet of paper bonded onto some mineral wool. But that's enough to retard. It stops this big convection loop and it breaks it down into a smaller size that doesn't then have enough force to get the loop going. So there's some really simple ways of addressing some of these things potentially, depending on the and then there's gaps in the research at the moment. What happens with cellulose insulation? Don't know. I can't tell you. We don't know. There's not.
Right.
Somebody, if you're writing a research paper and you're listening to this, email me. If wood fiber, there is some research on that, but again, it's a bit thinner on the ground. The interesting thing was that wood fiber seems to be a little bit more robust than certain mineral-based products. So yeah, one for the natural stuff.
Right.
So it's a bit of a new field. For me, at least, and it's examined in more detail in the document. So that's a good one to watch out for. And then finally, when there's the kind of what ties into the RIBA plan of work, which is the process workflow that we use in the UK construction industry. And incidentally, I'll make another quick cheeky plug for another document I've been writing. I've been writing the Passive House overlay for the RIBA plan of work, which sets out the framework for how passive house designers intuitively work, should we say, but formalizes it so that we can explain it to other parties, other groups. So I don't know whether within the AIA and another, and over your side of the pond, you've got a similar kind of workflow process, but we can, we can start to have conversations about that at some point. But inside the guide, basically, it's kind of highlighting some of these key things about how do we design for wind tightness and air tightness, encapsulation, which is the key concept at the end of the day. We need to make sure that the air barrier and the wind barrier are contiguous with the insulation, so there's no air gaps between the two. So encapsulation kind of really captures that sort of point of reference, shall we say. So that we talk a bit about how to deal with different planos situations and junctions and corners and penetrations, and kind of sketch out that. And then finally, we talk about site inspections and how to, what we might, almost penultimately, I should say, we talk about site inspections. And finally, there's that opportunity for what do we do about building performance evaluation? How do we measure what happens in practice and whether it's really working? And how can we nerd out about it and start to feed information back and forth. So again, there are some standards that we talk about and areas of interest, like velocities. If you've got a suitable probe, an anemometer, you can stick it in a cavity and tell us the velocities. It'd be interesting to find out what's going on inside buildings, so we can start to inform these standards and improve what we do.
Wow. Well, first, congratulations for this summarizing this very exhaustive kind of report on thermal bypass. Well done. And I think, there's, as I mentioned at the beginning of our conversation, there are these different levels of detail that you can dive into, which I think is really smart of you to do. There's there's this really thorough foundation that you've laid with the kind of review of the literature and presentation of that in each section, and then these key takeaways essentially with the practical implications, and then of course the translation of it all into the RIBA piece. I say, do people say RIBA, or is that wrong?
Yeah,
okay,
RIBA,
RIBA, yeah. People for AIA, nobody says so. So thank you. And this is I listened to a podcast called the Energy Transition Show with Chris Nedler, and he assigns a geek rating to each episode, and so I think that we'll this would have a very high geek rating, which is wonderful.
Yeah, I think we've spinal tapped this one. I think it goes all the way
yeah, right, up to 11. Definitely. We're clearly from the same generation. Your references land very well. So I think we're close to an hour in the conversation here, and so I need to let you get to your evening. I think it's nighttime there now. But is there anything else that you'd like to add before we finish up?
No, not really. I think that if you want to know more, I'll suggest that people go to the Passive House Trust, passivehousetrust.org, and UK that is, and look for the paper there. I'm sure you'll be putting a link in the show notes anyway, but if people are trying to go more direct. As I say, there is a general shout out. I treat this as a live document. So as much as it's kind of comprehensive right now, there's plenty of there's about 160 peer-reviewed papers cited, but there's more out there that may fill gaps in understanding and help us make better decisions. So if people are aware of things that are not in, I don't need to be resent stuff, so if it's not in the bibliography, then feel free to email something over, even if it's just a heading in the guide itself. It's got my email address, so you can reach out. And then so we can keep refining this and improving it to serve the community as a whole and the industry at large. There's been quite a lot of traction. In the UK, we've sent out advanced copies, and there are LETI, which is the London Energy Transformation Initiative. There's the Chartered Institute of Building Services Engineers. There's the Building Performance Network. There's who else have we got? There's the ACB and other organisations. There's about as well as the Passive House Institute, IFA, and others, Passive House Canada, and the Passive House Network in the US. Passive House.
Yeah, you got it.
And they've all kind of kindly supported this, in terms of said, yes, this is a competent piece of work. Right. So hopefully it's got broader reach, and it's got, in the UK at least, we've managed to get traction within industry outside of the Passive House circle. Because it's all peer reviewed. It's not trying to, shall we say, sell Passive House. It leads the research, points us in that direction, which is common sense to us Passive House types. So It's really, this document can also be useful for policymakers as well as developers, designers, and constructors. So it's kind of really broad, but people can it's not just that one whereby it's lip service. That it's founded on facts or a research base. So there's no conjecture in this. So people can make at least start the right conversations.
Yeah. Fantastic. Well, thank you for this contribution to the community. Really, it's really great work, and it's been great to have you on the podcast. Thanks, Mark.
Great. Thanks for having me back.
You bet. See you next September.
Well, like I said in the outset, Zach, it felt like I was in a masterclass there. Like
no kidding.
A building physics. Well, it was almost an advanced class. I think there was so much stuff in there. It's just I don't know where to start.
Yeah, no kidding. He is a powerhouse and thought leader, and I think that was pretty apparent in what we just heard.
I kind of, within the first couple of minutes of the interview, I kind of forgot that Mark was an architect.
Yeah, right.
Because his depth of knowledge of building physics and just physics in general is right up there, and he's explaining things that a lot of people, I don't think, realize how important they are. Right back to the gaps around insulation. A report that was done on construction, because we have a lot of that timber frame, sort of stick frame building here with fairly weight fiberglass insulations. That's kind of standard practice here. And some research was done a decade or so ago now of someone who went around to a whole bunch of building sites and had a look, just kind of observing and taking photos and measuring any gaps, tucks, folds, missing pieces of fiberglass, and rating those installation jobs of insulation on a standard that was being used at the time to measure the quality of retrofits. But these were on new builds, and they measured nearly 50 building sites separately, and the failure rate was 100%. So standard practice at the time, every single building site had somewhere around the pre-lining, somewhere there were significant gaps, there were missing pieces of insulation, there were pieces of insulation that had been squeezed in so much that they would have been ineffective. But it was just the builder, the main contractor on the site, just didn't even really see it as a problem, because it was just standard practice. And I would imagine it still is in a lot of cases, because those numbers, I think a lot of people just are unaware of the significant impact of gaps in insulation.
Right. And what he's describing are these tiny spaces between the insulation and the warm side of the assembly. So, and with those, with massive repercussions in terms of the thermal resistance of these assemblies. So, I mean, he's identifying a really critical area for improvement. It was pretty astonishing, really, to see some of those numbers.
I like the idea of thinking about tolerances, because we're very familiar with that in engineering terms and structural engineering. You have a known tolerance, because in the real world nothing is absolutely perfect. But as long as you know what boundaries that you're working within, then that's fine. And as Mark said, 5% sounds reasonable, but when then you look into the impact of gaps and air movement within insulation, and it's going so far beyond that tolerance that it would be completely out of spec if it was some sort of precision engineering.
Yeah, right. I mean, order of magnitude different.
Yeah. I mean, that it is large percentage changes of fairly small numbers, so it doesn't take a lot to have quite a large impact. But I think, I've certainly seen roofs where there are so many holes, either because of downlights or just because there's so much timber in the way, that the insulation, you can just tell it's effectively useless. That it's gone up there, but there's so many big holes and gaps, and there's drafts up there that it would make very little difference to the homeowner if there wasn't any insulation there at all.
Yeah, I was also struck, and I think I mentioned this in the conversation, but I was struck by how helpful it is to also have these in this report, which is this sweeping kind of survey of the existing scholarship around thermal bypass, right? And acknowledging that there are all sorts of areas that are where things are inconclusive, and but there are also areas where you can start to draw conclusions about how this scholarship should guide practice. So he intersperses these boxes in the report to help practitioners and folks digest the key takeaways. And then I think at the end, that with the RIBA plan, the RIBA plan of work, provides some really straightforward ways that architects can act on this information. So it's this. He's doing it. I think that's what is really great about this work that he's doing, is that he's kind of providing this bridge between, to some of us, fairly impenetrable research that's been done, then teasing out those places where there can be actionable, where there are actionable insights for practice. And that's a really important thing on these, an issue of thermal bypass that can have such, big impacts on building performance and durability.
Yeah. I mean, it's a pretty dense material in there, packed with a lot of information and a lot of helpful statistics. So, people might have to go back and listen to a couple of times, or head over to Leap and wherever else to get a copy of that. The report, plus along Mark's other work. I mean, Mark's produced a lot of other stuff, some great content.
That's right. So Mark's work, this paper is published via Passive House Trust. So I'll include a link for folks to the report itself, and there's a lot of great stuff there. So check it out.
I want to do a quick shout out to Norway.
Yes, no kidding. They're on it with thermal bypass.
Were they? Since before 2000, I think he said that there were calls back in, was it 1997 or something, to start requiring air tightness in buildings. Before he then got down into sort of the perhaps dynamic need for different air change rates depending on insulation levels. But I mean, having that insight and that push in the building sector, established for a while now, that's very impressive. And they've also, like you mentioned, gone the way that Fierce has already gone, making it a metric of permeability instead of air changes. So they've really taken leadership role there.
Yeah. And just the awareness of the impact of wind tightness, at that early stage. Yeah, definitely.
Yeah. We were never going to cover all of that in a summary. I think we could probably sell that off as a masterclass and training. You could take a week-long building physics course, or you could just listen to Mark for an hour.
Yeah, definitely. And I loved his Spinal Tap reference. You may be too young for that, Matthew. I don't know. Spinal Tap.
Yeah,
it's good stuff.
Awesome. All right. What have we got coming up?
Well, this coming week we have a presentation called that's on a Kentucky FIAS project, highlighting design strategies and off-site fabrication methods. And this is presented by Tom Bassett-Dilley of TBDA and Sai Safi of Uber Green Spaces and Homes. Both Tom and Sai have presented at Passive House Accelerator Live, but separately. But they're working together on this project and on this presentation. So that's going to be a project showcase edition of the show. Also, for folks who live relatively close to New York City, if you can hop on a train and get yourself to New York, we're doing an in-person event, which is really exciting that we get to start doing in-person events on October 13th in collaboration with the fine organization called Brick and Wonder. And the presentation, it will be doing a high performance building case study and cocktails at Brickworks, New York City on October 13th at 6 p.m. Eastern. And it's free. So this is a chance to hear from designers at Cook Fox about the Betances residence, which is a passive house, affordable housing development in the Bronx. Michael Ingui will be, the founder of Passive House Accelerator, will be playing the role of moderator and MC, and there will be some other big names there as well. So great chance to take in some exciting new passive house information and connect with other professionals. So I'll do a link in show notes.
Awesome. As always, so much going on, and we've got some other interviews lined up. Kim and the team doing some great work in the background. So look forward to that. We'll be back again next week on Passive House Podcast.